The acids and bases section of the chemistry paper starts with multiple choice question 1.7, which reads the conjugate base of HPO4 with a charge of 2- is, and we are given various options. What's important to remember here is that a conjugate acid-base pair is related by the gain or loss of a single proton. And when they ask us for a conjugate base, that means that the substance that we are given is an acid, because this acid will have a conjugate base. And an acid is defined in this theory as a proton donor, meaning something that will give away a proton. In this case, HPO4 has only one proton to give, and therefore once it has given that proton, it will just be left with PO4 with a charge or valency of -3, which means then that the correct answer is option B. Question 7 reads, ethanoic acid, CH3COOH, is an ingredient of household vinegar. 7.1.1, is ethanoic acid a weak acid or a strong acid, and give a reason for this answer. And 7.1.1, the answer there is very simply that this is a weak acid, because we only will encounter 3 strong acids. Those are hydrochloric, sulfuric, and nitric acid. And so any acid that is not one of those 3 is automatically classified as weak. And the reason for that is that it does not ionize completely. It does not ionize completely. We know by definition a strong acid is one that ionizes completely in water. And our explanation for why something is a weak acid in this or at this level is that it simply does not ionize completely. Question 7.1.2. An ethanoic acid solution has a pH of 3.85 at 25 degrees Celsius. Calculate the concentration of the hydronium ions, H3O+, in the solution. And we use our formula that is given in the data sheet for pH, which says pH is the negative log of the hydronium ion concentration, where the pH is given as 3.85, and that is once again negative log of the concentration that we are looking for. And so we can solve for this by seeing that it is 10 to the power of negative 3.85. Very simply, the hydronium ion concentration is then 1.41 times 10 to the power of -4. This being a concentration, the units are moles per cubic decimeter. Question 7.1.3, sodium ethanoate forms when ethanoic acid reacts with sodium hydroxide. 7.1.3 asks, will the pH of sodium ethanoate solution be greater than, less than, or equal to 7? What's important for us to realize is that this is a reaction between ethanoic acid, that we have already said is a weak acid, and sodium hydroxide, that being NaOH. And sodium hydroxide is one of the 3 strong bases that we will always deal with. And since it is a reaction between a strong base and a weak acid, we know that that is going to form a basic solution. And a basic solution is always going to have a pH that is greater than 7. We know that bases have pHs greater than 7, usually between 7 and 14. So because this is a reaction between a weak acid and a strong base, the pH of the resulting solution is going to be greater than 7, or it is going to be a basic solution. Question 7.1.4 asks us to explain the answer to 7.1.3 with the aid of a balanced chemical equation. And so what we need to show here is we need to show the hydrolysis reaction, where we know that a hydrolysis reaction is a reaction between a salt and water, where the salt that is formed in this reaction is given to us as sodium ethanoate. And there are 2 possible hydrolysis reactions. The one is the reaction between the sodium ion and water, where there is no reaction possible. And the other is the reaction between our ethanoate ion and water. And we can see here that that ethanoate ion is going to take back a hydrogen ion or a proton, which then leaves the water or converts the water into a hydroxide ion. And since we have a salt that is producing hydroxide ions in solution, we say that this is a basic salt. So this is the balanced equation that we give over here, where we say that the reaction of our salt with water produces hydroxide ions, and then our explanation is that we say, since there are hydroxide ions present, the pH of the solution is going to be greater than 7. Question 7.2. Household vinegar contains 4.52% ethanoic acid, or CH3COOH by volume. A 1.2 gram impure sample of calcium carbonate is added to 25 cubic centimeters of household vinegar. On completion of the reaction, the excess ethanoic acid in the household vinegar is neutralized by 14.5 cubic centimeters of a sodium hydroxide solution of concentration 1 mole per cubic decimeter. The balanced equation for the reaction is given here. Now, before attempting to answer this, what's important to see is that there are two reactions that are taking place here. The first one is a reaction that takes place between the vinegar and the calcium carbonate. Now, the vinegar, the only part of that vinegar that is going to react is our acetic acid. So the first reaction, I'm drawing them in two separate containers, is the reaction between vinegar and calcium carbonate. And what happens there is that we are told that on completion of the reaction, the excess ethanoic acid, what that tells us is that since the ethanoic acid is in excess, it means that the calcium carbonate is our limiting reactant, which means that it is used up. The calcium carbonate is used up in this reaction, or we can say it reacts completely with the acetic acid. Then the second reaction is what I'm going to draw in the second container, but essentially what this is now seen as is that there is still some acetic acid that remains. And in order to find out how much acetic acid that there is that remains, we react it with the sodium hydroxide. The sodium hydroxide. The reason why we do that is because we know the concentration, we know the volume of sodium hydroxide, and therefore we know the number of moles of sodium hydroxide. Since we've been given the balanced equation for the reaction between sodium hydroxide and acetic acid, and we can see that the ratio there is 1:1. If we know the number of moles of sodium hydroxide that reacted, we will then find our number of moles of acetic acid that was present here. What that then tells us is that the number of moles of acetic acid that is present in the second reaction must be the amount that was left over, the amount that was in excess from the first reaction. So we're going to start at question 7.2.1, which asks us calculate the number of moles of unreacted ethanoic acid. And we do this by seeing that our ethanoic acid reacts with sodium hydroxide. We can calculate the number of moles of sodium hydroxide. Now, it's important in these questions because there are so many substances present, it's important to show what exactly we're calculating the number of moles of. So I've said in brackets here, number of moles of sodium hydroxide, and that is equal to the given concentration multiplied by the volume, where the concentration is a 1 molar solution, and the volume is 14.5 cubic centimeters, where we remember that needs to be converted into cubic decimeters, and we divide by 1,000 to find that it is a volume of 0.0145 cubic decimeters, which tells us then finally that there are 0.0145 moles of sodium hydroxide that are reacted with the acetic acid. Now, the questions asked us how much ethanoic acid, not acetic acid. The question asked how much ethanoic acid there is, and we determine the amount of ethanoic acid by saying we can see that our ratio of sodium hydroxide to ethanoic acid is a ratio of 1 to 1. This comes from our balanced equation, and therefore, since we used 0.0145 moles of sodium hydroxide, that must mean that there are 0.0145 moles of ethanoic acid. Question 7.2.2 reads, calcium carbonate reacts with ethanoic acid according to the following balanced equation. Calculate the percentage calcium carbonate in the impure sample if 1 cubic centimeter of household vinegar has a mass of 1 gram. And so we start here with the only thing that we can do, where we can see that 1 cubic centimeter has a mass of 1 gram, which gives us a hint with what we can do, because we were told that we started with 25 cubic centimeters of vinegar, which immediately tells us that we started with 25 grams of vinegar. Now, that's not particularly useful, except for the fact that we know that vinegar is 4.52% ethanoic acid. So we can therefore calculate our mass of ethanoic acid in the vinegar by saying that 4.52% of 25 grams is going to give us the amount of ethanoic acid, and that tells us then that we have 1.13 grams of ethanoic acid that is present. This is also not particularly useful, but it does lead us on to what we can do next. And what we can do next is we can calculate the number of moles of ethanoic acid that is present, because we have the mass and the molar mass for ethanoic acid, and we can use the formula here, 1.13 divided by the molar mass for ethanoic acid, which is 60, and that tells us, therefore, that there are actually 0.0118, excuse me, that is 0.01883 moles of ethanoic acid. The reason why this is useful to us is because it tells us that at the start, we had 0.01883 moles of ethanoic acid, and then a certain amount of that reacted with calcium carbonate, and then we were left with 0.0145 moles of ethanoic acid. What that tells us then is that we can calculate the number of moles of ethanoic acid that reacted, because if we know how much we started with and how much we ended with, we can say the number of moles that reacted is then the starting amount, 0.01883, minus the end amount, 0.0145. And if we use the unrounded numbers, we find that that is an amount that reacted of 0.0043 moles. We can use this amount with the ratio of our ethanoic acid to the calcium carbonate, which is given by the balanced equation, which we can see is a ratio of 2 to 1, to see that if we used up 0.0043 moles of ethanoic acid in this reaction, we must have formed, again using the unrounded numbers, we must have had initially 0.00217 moles of calcium carbonate present. And now this is useful to us because that means we can then calculate our mass of calcium carbonate now that we know the number of moles, which is our number of moles multiplied by the molar mass, number of moles as we have calculated 0.00217 multiplied by the molar mass of 100. And that then tells us that we actually had 0.217 grams of calcium carbonate. And now that we know how much calcium carbonate there actually was present in this initial sample, we can calculate the percentage purity or the percentage calcium carbonate in the given sample by saying that is the actual mass, 0.217 grams, divided by the mass that was given, the total mass, which was 1.2 grams, where we were told it is 1.2 grams of an impure sample. And because we want that to be a percentage, we multiply by 100 to find that our percentage purity, or the percentage calcium carbonate, was 18.08%. This question, when marked according to the marking guidelines at 7.1.1, there's 1 mark allocated for identifying this as a weak acid and 1 mark for then explaining that it is not or does not ionize completely in water. When asked to calculate the concentration of hydronium, there's 1 mark for correctly writing down the formula as given in the formula sheet, 1 mark for the correct substitution of the pH, and 1 mark for our correct answer where the correct units are required. Question 7.1.3, 1 mark allocated for greater than. Question 7.1.4, we've been asked to explain with the use of a balanced equation. And so we got 1 mark or 2 marks for our balanced equation. And the final mark was for explaining that the pH is greater than 7 because there's excess hydroxide in the solution as a result of the basic salt that is produced. Question 7.2.1 allocates 1 mark for the correct conversion of 14.5 cubic centimeters to 0.14 or 0.0145 cubic decimeters, and then 1 mark again allocated for showing that we understand the ratio of sodium hydroxide to ethanoic acid, 1 mark for that, and therefore 1 mark for our final answer to say that there are 0.0145 moles of ethanoic acid produced. Question 7.2.2, there was 1 mark allocated for determining the mass of ethanoic acid that was present, 1 mark for using this formula to calculate the number of moles, 1 mark for correctly finding the molar mass of acetic acid as 60, and then 1 mark for realizing that once we know how much ethanoic acid we started with and how much we ended with, we could calculate the amount of ethanoic acid that reacted. We then got a mark allocated for correctly showing the ratio of ethanoic acid to calcium carbonate, where we then correctly substituted that using this formula over here. And then our final mark here was for calculating the percentage purity or the percentage calcium carbonate present in this. And importantly, 1 mark for showing that calculation for how that percentage was determined.